Hello, I'm Dr. Stacey Lyle. This is a podcast on the map projections and plane coordinate datum for the Florida Surveying and Mapping Society. I'm being joined by Dr. Dewitt, who has recently retired from the University of Florida. Welcome, Dr. Dewitt. Tell us more about your retirement. What are you going to be doing next?
Well, the first thing I'm going to be doing is a fifth edition rewrite of the Elements of Photogrammetry text with Dr. Ben Wilkinson. We've already, started the legwork on that, got the contract worked out, and he's going to be taking a sabbatical. I've retired. He's taking a sabbatical in the spring, and we're going to dive into really doing a good rewrite of that textbook. So that's
Yeah.
first.
Well, yeah, and you mentioned, and we've talked before about the fact that this surge of photogrammetry now with all these drones that are out there. Do you think you'll add more about using some of these aerial platforms in the book?
Definitely. In fact, if you look at the history of the editions of that textbook that Paul Wolf started, oh goodness, I think it was 1974 was the first edition. It was Elements of Photogrammetry for the first two editions. And then the third and fourth editions, there was kind of like a tagline added. So it was Elements of Photogrammetry with Applications in GIS. And in discussing with Ben, we felt that, our level of knowledge of GIS and what we could put in a photogrammetry textbook just wasn't really up to speed with the rest of the GIS literature. But drones and close range photogrammetry, on UAS, kinds of systems are definitely becoming more popular. So we worked with the publisher, and they are allowing us to tweak that title. So it will be called Elements of Photogrammetry with Applications in Drone Imagery.
Nice.
And we're going to have, we'll have a new chapter on, specifically on drone photography. And then, of course, the principles of, data reduction and calculations and such will be kind of sprinkled throughout. So yes, there's definitely going to be an increase in drone imagery material.
So that leads us to our topic here of coordinates, and the value that photogrammetry is that we have a coordinate for every one of those pixels, so we can do a lot of digitizing and mapping and things of that nature. But if we jump in and look at the aspect of the history of using coordinates, right? Surveyors historically did not always use coordinates, because you could do a survey and make a plat with just the bearings and distances. But now that, we get coordinates instantaneously from our GNSS or these photogrammetric methods, we're moving to where coordinates are being used more and more, even regulatory. What's your thoughts on that?
Well, originally, property boundaries, people's occupation lines and so on, they had to be defined with something that was physical and that they could see, with monuments at the corners and be able to walk out there and actually see the lines on the ground. If you were to describe these locations in terms of, X equals Y equals, most people wouldn't have any idea of what that means. So, property surveys were really just kind of locally connected to, the local monumentation primarily. Another aspect is geodetic surveying or worldwide surveying, where you're trying to figure out, think of navigators crossing the Atlantic, trying to figure out their way, going from, Europe to the New World and trying to navigate. Well, they had to be able to figure out where they were, not based on monuments they can see on the ground, but they were using mainly like star navigation and figuring out where they were in terms of latitudes and longitudes, which are coordinates. And those systems, the geodetic, position on the Earth, and the physical connection on the ground were kind of loosely connected, throughout the years. There wasn't a real strong tie between the two, but largely with the advent of GPS and GNSS, the ability to measure, like you say, pretty much instantaneously to within, maybe a centimeter or thereabouts, you can actually kind of connect the two now, where you can very precisely put coordinates on those physical monuments. So not only can you have something physical that people can see, but they can also be put into a very precise coordinate frame so they can be lined up with other measurements and systems. Perhaps the infrastructure, the utilities, sewer lines, all that kind of thing, they can be superimposed and accurately represented with respect to each other once you make that connection between the physical, monuments on the corners of their property and the geodesy that gives it the coordinates.
So when you are trying to retrace a survey and go back and look at what was done in the past, and they used some bearing and some distance, I would have to, figure out which north they used and kind of go from there. But regardless of the north, I could use the difference in angles around that property and retrace it. Now that we require 2 points on the property that were surveyed, and I might use a base station from one vendor, or I might have my own base station, or I might use, a different coordinate systems, and they might be off a little bit how I did them. Do you see that as a problem, or do you think that just when we have those coordinates, we can use those absolutes to try to then reproduce the property? Or do you think we need to be very absolute in the coordinates?
Well, that's kind of a tough question to answer. I mean, we do need to be careful. Once you start getting into people's property, they're not going to be satisfied with a coordinate system that has an error of 5 feet or something. No, they want their property positions to be known more precisely. Using the appropriate datums. A lot of professional surveyors that I talk with, they definitely understand, North American datums, and how they get coordinates and so on, but they may not fully understand the subtleties between, one epoch to another, or the coordinate systems that actually have a time component and allow for the movement of plates of the earth and so on. Once you start getting into the sort of the details of the high-end geodesy, not everybody has that level of knowledge and background to be able to handle them properly. So you absolutely have to be careful, particularly if you're establishing property lines purely in terms of coordinates. If you don't put a monument down, then that would really be a dangerous thing to do. People, I can't think of a situation where a property owner wouldn't really care to see a physical monument marking their corner so they can see it with their own eyes. If you just show them a display on an RTK receiver and say, here, there's your corner, this is where we are, we're at your corner, I don't think a lot of people would appreciate that. So it is going to be very important to have, be careful, precisely define the datum, make sure you use the correct epoch, the year of it being, established, and make sure you're doing an apples to apples comparison or an oranges to oranges comparison.
Yeah, that makes a lot of sense, because in the future, say 40 years from now, and I'm trying to retrace your property, if I'm trying to match your coordinate and I'm using my new coordinate system, right? I have to get all the conversions and transformations and know the time period you did it, right? And so you need to let me know that and which one you use so I can try to convert to that one. but there's still going to be some potential problems because the plates of the earth are moving and there's lots of other issues. That's where you still need that physical monument along with that.
Right.
Do you see a problem with, well, if I give the coordinates of property corners, the landowner's going to use their cell phone and go out there and try to locate, or others, if I share that data?
Well, I'm not sure that there's anything that you can guard against that. A property owner is allowed to make decisions regarding their own property. You can't tell them, what they can and cannot do with their property. But for them to measure and I mean, people do that kind of thing. They'll try to essentially do a survey without actually hiring a surveyor or without being a professional surveyor themselves. And they depending on their knowledge, they may get fairly far into it and do a fairly good job, but they usually get tripped up on something down the road, whether it be a legal concept, a court precedent, that kind of a thing, or some of these higher end geodetic concepts, datums and crustal motion and all that kind of thing. There's been quite a detailed study of property boundaries and geodesy and all this surveying background. There's a lot of years of very sharp people studying that in great detail, and you don't just kind of, oh well, I can do that, without even it's the Dunning-Kruger effect, where you think you know enough, so you'll just kind of do something. It's once you start understanding more and more about it, you realize how little you truly do know. So you want to make sure that you know what you're doing before you start diving in with your cell phone and trying to measure coordinates, to property corners. I can understand a property owner wanting to do that, but my goodness, I would strongly caution them against it because it can be risky.
That's a good point. It kind of goes back to what you said earlier, that there are so many nuances about the geodesy aspect, right? And coordinate system in the epics, that even us as scientists and professionals, it's hard for us to keep up with it and know it. So you definitely could see the public have an issue. But let's go over to geographic, or sometimes called geodetic, or latitude and longitude coordinates versus northing and eastings. When we deal with, this GIS, geographic information system, and they want to get all of our parcels in a coordinate system so they can add it to their database, right? So which should I be doing? Should I be putting just state plane, or should I also put my latitude and longitude on there? What's your thoughts there?
Well, with an appropriately defined state plane coordinate system, you can have a direct conversion between latitude, longitude, and state plane XY, or easting, northing, precisely. I mean, it's a mathematical definition, so it really doesn't matter which one you specify. You can always, perfectly convert back and forth between the two of them, at least, mathematically, in theory you can. So, it doesn't really matter in terms of the accuracy of the coordinates, but when you want to use them in a GIS, the GIS, the software, they work with Cartesian coordinates, X, Y, maybe elevation for a Z, but their database isn't fundamentally based on a spherical coordinate system, an angle above the equator for latitude, an angle along in the equator from the prime meridian for longitude, and then an elevation above the earth for height. That's a different kind of a coordinate system that's not used in the GIS software. But the bottom line is, with an appropriately defined plane coordinate system like state plane coordinates, you can use that for a GIS database within, some region of interest, whether it be maybe a municipality or a county, perhaps even statewide or regional areas, even, across the US. You could, you wouldn't use individual state plane coordinates, but maybe a more global kind of a coordinate system or UTM or something like that.
So historically, where we've had, like the NAD 27 latitude and longitude, and then we came up with the NAD 83, their values are significantly different because the way that we cast or place that latitude and longitude lines on the Earth, trying to reduce our scale in North America. So if I get one coordinate of one system and another system, you can see that you'll be quite a ways off. But when we go to NAD 83 latitude and longitude, and we look at WGS 84, which is the coordinates you would go on your Google map and get, for example, those are really close to the point that they could make a mistake if the public was just trying to utilize those latitudes and longitudes. Do you see that we need to be clear that when we're using the Webb Mercator 84 latitude and longitude versus the NAD 83 latitude and longitudes? What's your thoughts there?
Well, I think most of that is going to be handled, at least I'm kind of hopeful, that it'll be handled by appropriate professionals, surveyors and engineers, when they're dealing with property and infrastructure and so on. Even in a GIS, I don't know how often the public would get their hands on coordinates, state plane coordinates and start working with them. They may see plenty of maps. There may even be a coordinate grid sort of superimposed on it, but they often, they generally won't get down into the level of coordinates on individual points, I don't think. However, it is critical that, like I say, the surveyors, the engineers, the people who use those coordinates to actually, physically install things into the ground, it's critical that they get those positions accurately, at least for highly precise engineering kinds of, structures and things that have to be constructed very accurately.
So, going between the two datums, it's not a simple coordinate calculation like it was going to latitude and longitude to northern eastings, like you talked about.
Right.
And actually in your book, it does it well by explaining transformations. Can you discuss transformations and the problems with them and what we should be aware of?
Well, if I can, maybe I'll talk about this based on the NAD 27 datum definition. So in the middle of the U.S. at Meads Ranch, they defined a latitude and longitude, and then an azimuth to a nearby Point Waldo, and then connected all sorts of surveys going across the U.S. to that fundamental, you can think of it as kind of like an origin. Now, as with the measurements that are close to where that is, it's in Kansas, you're pretty close. So if you had some measurements and you were making some errors, you wouldn't have a large propagation of error into your computed values. But by the time you work those measurements connecting from one line to the next and measuring distances or angles or whatever you're doing, and you bring it down, like say from Kansas down to Florida or over, up into Alaska or something, going a long distance, you've made a chain of measurements that all have errors in them. And then the accuracy just deteriorates the further and further away that you go. So, if I'm looking at a set of coordinates in Florida here, not only do I have sort of this underlying, spherical or spheroidal Earth geometry thing happening, the sort of the geodesy part, but I also have all the measurement errors that have been built up to the local location, let's say in Florida. Well, if you're going to transform from one datum, let's say NAD27 to NAD83, a more modern datum, what you're effectively doing with that transform is, to an extent, you're modeling measurement error. You're modeling the local error from the accumulation of measurement errors that came down from Meade's Ranch, and relating that to the much smaller measurement errors that were inherent in the NAD83 system, because they had more modern measurements to do with them. You're not really working with geodesy or the underlying, three-dimensional nature. It's just working from one set of, easting northing to another set of easting northing, each having two different sets of distortions in them, and trying to get the best match from one to the next. So that's a transformation. Well, as opposed to a conversion, which is, it's an exact mathematical, like if I like to explain to students as, think of polar to rectangular. Polar is an angle and a distance, and rectangular is an X and a Y. And you can, you use your, distance times sine theta and distance times cosine theta to get the two, coordinates, or you could do the inverse tangent of, change in Y over change in, I mean, you can directly calculate those things. There's no measurements involved. There's no, theoretical errors, probability, any of that kind of stuff. It's just pure math. Those are conversions. So transformations deal with modeling of measurement error of some sort. Conversions are purely mathematical calculations.
So one of the transforms that we use commonly in North America is NADCON. And, like you said, if it was simply a formula, it would be an easy equation. I noticed that when I use NADCON, it's a large file. It must have a lot of data. It must have the model of one and the model of another throughout the whole US, and then uses the data around me, correct, to build my transformation equations, if you will, locally to where I'm at. So that's why that file is so big. Is that correct?
That's sure. Yeah, exactly. I mean, I talked about all the measurement errors that would have accumulated as you went from Meade's Ranch down to Florida. Well, you've got the measurement errors going to Maine and up to Minnesota and over to Washington State and out to California. I mean, in all these different areas, you get different amounts of error and distortion and so on. You need to know what it is at all those locations. So yes, exactly. You have to have knowledge of the coordinates in those areas in order to be able to do that transformation. So you have to have all that information there. Whereas a simple conversion, all you need are the few mathematical parameters and the right set of equations, and you just plug and go. And there's no local distortion effect, modeling errors, any of that kind of stuff.
So going on to the simple conversions, you're really now talking about projected coordinate systems, or projecting a plane onto the sphere, right? And right. Across the U.S., we use a lot of different projections, and each state has their projections like we do here in Florida. Those projections are made so that if I take a difference in latitude and longitude across the sphere, and I take the difference in northing and eastings, they should be very close, right? Not way off in their distance and be out in what we would consider scale. Is this what we do with these projections?
Well, yes, and the National Geodetic Survey provided to all the states kind of a recipe for setting up these local state plane coordinate systems, and you get individual little zones in the different areas that will have definitions for their coordinates. The Lambert coordinate system, projection for Florida, we would use that in the panhandle of Florida because it's a long east-west portion, and it fits well with this Lambert. But depending on where you are in your state, it will give you the appropriate projection for that state or that area, and the key constraint that they were operating under is they wanted to make sure that the distance distortion, which I think is the distortion you're talking about, is no more than 1 part in 10,000 between any points in that entire zone. And if you think of 1 part in 10,000, if you measure a 10,000 foot line, that would be 1 foot. If you measure a 100-foot line, that's 1/100th of a foot, or about 3 millimeters. 1 part in 10,000, that's quite small. And if you're talking about, let's say, a typical property, somebody has a lot in a subdivision, maybe roughly 100 feet by 100 feet, the difference of distortion of distance might be as much as 1 part in 10,000, often much smaller, but it would be 1/100th of a foot, about 3 millimeters, a little tiny piece that probably isn't going to matter much, even to a property owner worried about corners and such. As you expand that size, maybe you're dealing with, let's say, a construction project where you're building some sort of connector from point A to point B, and they're 5 miles apart. Well, now 5 miles, that's very ballparkish. 25,000 feet. So 1 part in 10,000 there would be about 2.5 feet. So yes, you better take that into account, because that's a fairly substantial, that 1 part in 10,000 over a long distance can give you that fairly significant difference there. A long time ago, when I was a rookie professor, it was maybe a couple years after I'd been down here, and one of our alums, a very recent graduate who had me as a professor, called me, and he said he had a job. He was working for the company, and they were tasked with establishing state plane coordinates on a highway project. And then the contractor, at least this is the way the story was relayed to me, had somebody set up a total station on one point and a reflector on another point, and measured a distance in between. And the measured distance on that, from the total station, was off by about 1/2 a foot from the calculated difference in state plane coordinates between those 2 points. And the contractor was telling him, "You guys messed up. You made a mistake. These distances don't check." And he thought he was doing this correctly and giving state plane coordinates, but and it was correct, for a long distance. And it was I think he said it was about 1 mile measured distance. It was appropriate to have, in that case, about 1/2 foot difference between the ground measured value and the state plane measured value. And, now I didn't tell him how to try to explain that to the contractor, because, that can be difficult to explain that to a lay person. Although I've been kind of thinking about this, and really, to a large extent, what this amounts to is, when people are talking about distances, they're typically talking about horizontal distances, same points at the same elevation, just a horizontal distance. And, here in Florida, we live pretty close to mean sea level. So if you look at, a horizontal distance measured on the ground versus a horizontal distance relative to I'll use the term, the ellipsoid, the approximate shape of the Earth, there's virtually no difference. They are about the same. But if you go out in Colorado and you're out in Denver, the Mile High City, you're not at mean sea level. You're way above. And you've got lines that project from the center of the Earth and diverge and go up to the heavens above. So depending on where you are, what elevation you're measuring that line, you're going to have a different length showing up. And going, out in Colorado, you're going from ground level, maybe down to the ellipsoid. Okay, that can amount to as much as 1 part in 4,000. So it's even worse than the 1 part in 10,000 of the state plane distortion. So, you absolutely have to be careful of reducing a measured ground distance to a geodetic distance in those areas. Well, here in Florida, and there was a discussion, quite a few discussions about the new state plane coordinate systems. And I suspect you're going to want to get into this, but there was a talk about creating one coordinate system for the entire state. And if they did that, first of all, it would have to be an oblique Mercator coordinate system in order to get the distortion fairly small. But even then, they could not meet that 1 part in 10,000. And I forget, I think it might have gotten as bad as 1 part in 3,000 or something if they went statewide. Now, again, it's a calculation. If I want to, if I want to convert from my state plane XY into my lat long, project it up to ground level and make accurate 3-dimensional calculations for my highway design or my structures or any of that kind of stuff, I can do that perfectly. No distortion, well, I shouldn't say no distortion, no measurement errors. You can make those calculations and get very accurate quantities from that. And I tried to convince my colleagues of that we really only need one coordinate zone, and we could, handle it with, making the appropriate conversions. But I was outvoted, I would say. They really did want to have, low distortion, areas. In fact, they were even concerned about that 1 part in 10,000. They wanted to tweak it and make it even better. And I think maybe 1 part in 20,000 or something is what we came up with the new zone. So there's all sorts of ways that you can approach this. And as long as you make the appropriate calculations, things can work out okay. But you have to be careful. And particularly, like you say, crossing from one zone to the next, strange things can happen when you go from one set of state plane zone coordinates to the one next to it. And all of a sudden, if you show it on a screen, like in a GIS, boom, they'll be sitting in 2 different places. And in order to fix that, you got to put them on a common coordinate system. In other words, perhaps create your own system for the entire state or whatever.
So not only do we have this distortion from distances, but we also have distortion of our angles on a globe with latitude and longitude. All the lines are converging to the North Pole. On a flat plane, they're going 90 degrees straight up and down on the flat plane piece of paper. So there is this difference between what we would say geodetic north, also true north, and the grid north. Now, as surveyors, why would I, need to know this? Well, if we're in the public land system and they have meridians or lines that are supposed to be ran true north, right? And I'm going up a section line or something like that, and I'm using a grid coordinate system, I could be off depending on where I sit on that projection. If I'm in the dead center, I might be going true north, but if I get way over to the right edge or the left edge of that projection, there's going to be a deflection of those angles. And it's important, if I'm trying to run these lines, right, that I'm running true norths versus these grid norths. You can calculate that correct and figure out exactly what that convergence angle is?
Oh, yes. And in fact, the NGS has online tools that'll help you make those calculations if you wish to use them. Other software can do that as well. And the key angle that you're dealing with is they refer to it as the mapping angle, the angle from the true azimuth to the grid azimuth, which, like you say, within a grid coordinate system, all the meridians are parallel, but within the real world, they all converge to the North Pole, and you've got that angular difference. If you pull out the old USGS topographic quad maps and look down in the border information, you'll see a little diagram, you'll look in there and it'll have a little north arrow, and then there'll be another one off at an angle with a little star at the end of it. That's a visual representation of where true north is for the star, as opposed to the grid north being straight up the sheet. So you can physically see that on that map sheet where that is, that relationship between the two. Now it changes largely with longitude. As you go east and west, that mapping angle is going to change significantly within the zone. It can also change in a Mercator zone as you go from north to south, but it's not as much. But you definitely have to take that into account when dealing with getting the correct azimuths on here.
Going back to the scale of the distance, all the math is going from the ground to the grid. We go back to our earlier statement. Now with GNSS, I get a grid coordinate in 10 seconds, and then I have to go up to the ground because, if you bought a mile by a mile, you bought a mile on the ground, not a mile on my grid system. And so you actually have to divide that grid distance by that scale factor to get on the ground. All of our math in our books and our textbooks show it the other way. You think it's because the way we used to survey was on the ground and we had to convert everything to grid? It wasn't that we got it within 10 seconds instantly?
I think that's probably part of it. I mean, when I think back on how I learned that stuff, we always, we were out there with and for us, it was steel tapes and transits, but nevertheless, we went out, we measured on the ground, and then they told us, okay, you're going to have to calculate, positions and resolve to horizontal distances and calculate coordinates. We were always going from the ground measurements down to some coordinate system and ultimately state plane.
You have a small area or small distance, they can accumulate it. As you talked about, if you were going from Gainesville to Orlando, that's a long distance, and that 1 to 10,000 would definitely show up. But if I did that in 100-foot, little bursts, it doesn't seem like it would matter, but it could accumulate, right? And eventually grow on me for that scale factor. So don't discount that scale factor just because you don't think you're going a very long ways. Would you agree with that?
Absolutely. And largely, as I mentioned before, it's relative. Think of that 1 part in 10,000. If you're going a lot longer distance, that 1 part in 10,000 can actually, end up being quite a bit. I also, I've been kind of thinking about that, reduce from ground to grid, and, not really going the other way. But what about a contractor? And let's just say I'm bidding on a construction contract out in Colorado, so it's mile high, and they want me to construct a highway that's 10 miles long. Okay. Now they give me plans that are done up in state plane coordinates, so I can get that distance on there, and let's say it is 10 miles right on the nose, from point A to point B in state plane coordinates. Now that contractor is going to say, all right, that's a 10-mile construction job. I've got, such and such pavement parameters and thickness and all that kind of stuff. I'm going to need these quantities to make that happen. But really what's going to happen is they've got to do this up on the ground. So they should be multiplying all these calculations by whatever the inverse scale factors are to bring them up to ground level, which might make those, let's say it was 10 miles worth of highway, that might be 10 miles plus 20 feet. Or I'm really just kind of grabbing a number out of the top of my head.
Right.
Do they put that into their calculations for the bid, or are they just going to figure, well, I'll eat this 1 part in, in Colorado, it could be 1 part in 4,000. The elevation factor, which is more critical than the state plane grid. I've really wondered about that. I suspect they don't really take it and tweak it that carefully, that there's enough kind of, slop in the process, plus or minus, that they just kind of, work through that. But theoretically, that would be the way to do it. If they want to precisely calculate those quantities, they would use the design plans, which are typically in state plane, very precisely defined with, some CAD system. They've got all the coordinates and everything. Now they've got to project it up to the real world surface where it's going to be constructed to figure out the real lengths they're going to be in place.
I can add that in pipeline construction, in my former working in the pipeline industry, they did go up to the ground because, as you can imagine, when you're doing pipeline, not just how much pipe should we purchase, but there's calculations on pressure and flow in pipelines where we have to have the true values, because not having the true values could change the pressures and flows and sizes of the pipes and how we do things. So we cannot not or work that slop, as you talked, into the equations there. So for pipeline construction, for sure, we need to have the true ground measurement or our calculations that we use in managing an infrastructure. Even if we looked across a whole county, that say that we have natural gas lines running through that whole county, if we are way out on the east side of the projection and you're using a GIS and all the pipes and everything is down here on the grid versus up on the ground, those are two different pressure models, right? You would agree with me that you would have to calculate?
I mean, you should at least be aware of it and check it. Verify whether it has an impact. You may find that, okay, in this case, it's not a problem. Although with the way software is nowadays, I would set it up so it always uses the appropriate computational procedure, unless that turns into being just too costly of an exercise. But usually that doesn't matter. Once you got your software system set up with the appropriate parameters, it's just hit the right button and you'll get your answer. So I think that it's very important to take those into account and at least be aware of them, so that you're not making mistakes, like you say, getting the wrong pressure model because you didn't project to the true distance.
So you mentioned earlier a statewide single coordinate system. You would think, okay, you could use UTM. Now, UTM is a global system where we are taking, 6 degrees of longitude and making these transverse Mercator projections across the whole U.S. But what we had found in, specifically, if I go back to the oil and gas industry with seismic, when we would set up our seismic models, if we used UTM, it put too much scale into those. And when you load seismic data, because it's so huge and so massive, it's hard for it to reproject on the fly like you're talking about. So even if you had used the UTM or something, you could use a conversion and maybe, fix those scales. They can't reproject the data. So it's a problem with them. But now going over to this new coordinate system, right? This ITRF that we're moving into, and it circles back around to what you said originally, this time stamp. Expand more about what you mean by time stamping now coordinate systems, and why are we now going to a new coordinate system?
Okay, and now there's sort of two main themes within our overall discussion. One is datums, and then the other is state plane coordinates. So now we're kind of going back to the datums thing. We're trying to get that model of the Earth concept, and in basic geology, we learn that the crust of the Earth, it consists of various plates that are kind of floating on a liquid mantle, and they move along, and some move underneath others, and so on. The surface of the Earth isn't quite as static as it looks like when you're standing on you stand on your front yard and you look at the street, so that's not moving. Everything seems solid to me. But, at velocities of, millimeters per year, there is some crustal motion. And if you're, let's say, on opposite sides of the San Andreas Fault, and you're looking at what happens to a property line across there over the years, there's been a sliding of those two plates relative to each other, two crustal plates, creating essentially a discontinuity. So depending on when you made measurements going, say across the San Andreas Fault, you're going to get different values depending on whether you did it back in the 1920s or the 1950s or 2000 or whatever. There's, there may be a few centimeters or perhaps even more with a fairly significant earthquake effect. The crustal plates move. So if we want coordinates on monuments that we place into the ground, we put in, iron pipes with, caps on them, or drive stainless steel rods down to refusal. We put physical monuments in the ground that we think is solid, but it's actually kind of floating on this mantle. And you try to put coordinate systems on something that's sort of floating, and that's a challenge. And you can do things like, okay, where are the plates right now at one instant in time, which is referred to as an epoch. So they say, okay, here's where the plates are now. We can define a coordinate system in terms of that time. But then, in theory, a year later, the plates have shifted a little bit, and there might be a couple millimeters of movement now. Are you going to go through and redetermine all of your coordinates and say, okay, we've got a new set of coordinates this year, folks. Things have shifted and so on. For almost all practical uses, that would be a real problem, to have to go back and change your coordinates almost, on the fly as you're going. So what they typically will do is use epochs and deal with a datum or a reference frame at a particular snapshot. And that's what the NAD 27, NAD 83, those were effectively snapshots, although they were created by using measurements that occurred throughout a span of years. So they're kind of a hodgepodge mix. With the ITRF, the idea there is you're trying to use the time the measurements were made, in addition to the model of crustal motion of these plates, and coming up with a coordinate system with a 3D coordinate set, actually latitude, longitude, and height, and time, that accurately quantifies where all the plates and everything are on the Earth at any one time. And that's this ITRF concept. So that's kind of behind it. We've got GNSS receivers on ground monitoring stations throughout the world, constantly tracking and updating and realizing, these are how the plates are moving. They're getting all this kind of stuff. And at any particular point in time, they can say, all right, you want to take the current epoch and say, that's the set of coordinates you're going to use. Go ahead, we can do that for you. And that's what NGS is kind of getting teed up at this point. The NSRS, they're trying to create this new spatial national reference frame, and they're going to set it up for a particular epoch. And that if you want to really, get high accuracy, coordinates related to, crustal motion, you're going to have to not only start with the coordinate that you had at the particular epoch, but then deal with how the crustal motion changes, how those plates move over that period of time to whatever the date is of your survey or your work. Again, those are things that, very few people have to deal with that level of precision and accuracy on the datums, but that's behind it. That's the NGS folks. The they get the real high end stuff, and then we'll release, say an epic for a datum, and have that available to just, not only just ordinary, lay people, but, engineers, surveyors, very accurate sets of coordinates to use for, long periods of time within maybe continental areas and so on. Then that's kind of that ITRF forms that basis.
Let's say that you have a GPS base station that I call up and I get my corrections from, and we're on this plate, and the base station is moving with the plate. And so when I do differential every year, I would say I'm measuring a road in my neighborhood, and every day I would measure that road, and I would not see that change because the base station is moving with me on the plate. So I don't see the change, right? But let's say that the plate is moving a meter a year. Well, okay, I would still get the same coordinate to go survey the road in my subdivision. But now when I jump in my car and start driving and it's showing me on top of the map, because, maybe it was 10 years ago and it's moving a meter a year, my car's now going to show me not on top of that road because the plate and the base station is moving underneath me, right? If you will, with me. I now see myself in a different location.
In theory, that's what happens when you have this crustal motion. Although, again, if you think about it, we're talking about, maybe millimeters per year or a centimeter per year in most cases. I mean, it's such a tiny amount that it's hard to discern until you make, like decades of jumps. Like, okay, from 1960 up to 2023, okay, there's been maybe a half meter of shift along a particular location. Now we should probably take that into account. I don't know that you could, it's probably not feasible financially to be able to go back and actually update everything, in real time as the crustal motion is taking place. I don't think it's really that critical to be dealing with the coordinates, updating in real time like that. But certainly if you're trying to piece together, historical pieces of information, a survey from the 60s and a survey from the 2023, and okay, there's a bit of a shift here. Yes, you do need to take that into account. I kind of wonder, they talk about, there's a big earthquake upcoming for California at some point. San Andreas Fault is very kind of flaky and could shift. If that thing shifts, 5 meters, so they're going to have to update maps. They're going to have to update, it's certainly people working in that area or living in that area are going to want to see what's currently there as opposed to what used to be there. So, yes, they have to deal with that. Usually it doesn't happen that abruptly. And those changes are just so subtle that it's really hard to discern.
There's a good example in the oil and gas industry. The Australian plate moves quite a bit. It's in decimeters a year. And they had used a base station and went out and set a rig. And then like 30 years later was going to set a rig right beside it. So they used the same base station and the same coordinate that they had here, and when they go to change it, well, that base station had moved. And where that rig was sitting at now, was different. And so they actually had made a walkway to go between the two rigs, and it was somewhat like 2 meters too short. So when they brought it out there, it didn't fit.
Oh my goodness!
Find out is this shift.
The tectonic plate that covers most of the the coterminous 48 states, other than way in the west, part of California and so on, most of that is a fairly solid, rigid plate. it kind of floats a little bit and maybe rotates a little bit. But like you said, if you have a base station in one location and a rover, somewhere else within that plate, they may have slightly rotated a little bit relative to the world, but they're still in a very tight relative position, compared to each other. And that's, effectively what they're doing is they're going to have kind of like zonal datum things that you can work with. If you're working with this Eastern US plate, I forget exactly the technical term they use for it, you can work within that zone and essentially not worry about shifts of tectonic plates, because it's just probably immeasurable, at least with our current technology. But if you're crossing a boundary from one plate to the next, that's where you really have to watch out. Like you said, with the down in Australia with the oil platform, if you're on opposite or on two different plates and enough time has elapsed, you're going to get an appreciable shift in positions from that. So anyway, the gist of that talk that I saw there, as long as you're within this eastern plate for the U.S. and work with that as your coordinate system, you can pretty much work with that epoch, and it'll last for a very long time until they may come up and start changing parameters, rotations, and such.
Very good. Okay, so let's go over to vertical datums.
Mm-hmm.
So we have two vertical datums, NGVD 29 and NAVD 88. These are vertical datums separate from the horizontal, and we use these a lot for flood mapping, right? And elevations and topos. In today, we obviously want to use our GNSS everywhere we can, but the GNSS can only tell me how high I am above or below that perfect sphere. Also, we call it an ellipsoid, and it can give me that ellipsoidal height, and it can give it very precisely, but that's not tied to sea level. So to tie it to sea level, we need to get an idea of, how high we are above or below at that specific spot of that ellipsoid. And what we've done is used gravity, right? And measured gravity at sea level, and then gravity, like you said, up in Denver at a mile high, it's going to be a difference. And so using gravity, you can get me within 15 centimeters of sea level, right? And then from there, I use the precise portions of what GNSS, which can do centimeter, and I topo the whole location. If I apply that geoid model, now I'm going to be, approximately to sea level using that way. So now we have all these gravity measurements that were made along railways and highways, and it's like you shot topo just randomly everywhere.
Sure.
And then tried to make a surface model. But they're moving more to now airborne gravity, which would be almost like a LiDAR, where it's very systematic and uniform. I mean, we've had satellites that could do gravity uniformly, but they're way up in space, and so they're very coarse. Do you see us moving now towards this future geoid models where we are having just a perfect airborne gravity, or do you still see us using ground measurements to make geoid models?
Well, oh my goodness. You can make so many more measurements by, flying an aircraft with a, gravity gravimeter in it. And like you say, kind of using LiDAR, flying back and forth and getting your measurements that way, as opposed to point measurement, taking a single gravity meter and measuring at individual points. Yeah, I mean, you're going to get overwhelmed with the airborne data. So you're going to get, better accuracy just by having wider coverage and more thorough coverage with this thing. But the bottom line is, or at least I like to kind of think of it as, mean sea level seems like a very convenient concept. What it means sea level, that must be a nice elevation 0 point. That's where it should be. It's the mean, the average level of the seas. But if you think about it, my goodness, what really is that? If you walk out to the beach, on the Atlantic coast, and you watch the ocean, it's not level. It's not a constant position. There's tides, there's waves, there's flow, there's the Gulf current. There's what you might think is an equipotential elevation of mean sea level. Technically it's not a gravity surface. Mean sea level was fine when they were navigating sailing ships across the Atlantic and such, and trying to figure out where you were on those bases, in that basis. But once you start getting into you're talking about using GNSS, where you're actually measuring position above the ellipsoid and trying to convert it to something, do you use mean sea level? Well, the geodesists tell us, no, you don't use mean sea level. What you use is a equipotential gravity surface. That's the theoretical concept that makes more sense for a 0 for your elevation than mean sea level. And again, we're tweaking small amounts here. It's not like kilometers or even tens of meters or that. We're tweaking kind of small values, going from mean sea level to a true equipotential gravity surface. But ultimately, that's what we're building in these vertical datums. And I'm kind of stretching the limits of my geodesy knowledge, but as I understand it, NAVD88 was also a gravity datum, and then they converted the gravity to elevations for people to use. And effectively, they're going to be doing the same thing, but for the new reference system. But essentially, they're creating a better gravity model and a new geoid model, which will give an accurate transformation, if you will, from the elevations determined from GNSS down to an elevation from an equipotential gravity surface, which is what we want. We want elevations to be based on, or we want to be able to determine flow of water, gravity flow for sewer lines and such. That's based on, equipotential gravity. That it's the physics that deals with that. It's not some mean sea level that has some kind of fluctuation, little ocean currents and other things. So yes, we're definitely moving to where the basis of the datum will be gravity measurements, but the real manifestation for those of us who use it on the ground will be elevations, these orthometric heights that we can use for our benchmarks.
I recently had a podcast with Richard Allen, and we were talking about FEMA flood certificate. He's the city flood surveyor in the city of Orlando.
Yeah, I know, Richard.
And he says, it's fine. You can use your GNSS and your geoid model, to get this elevation. But it kind of goes back to what you said originally with this modeling the earth, the data modeling the earth and the points on the earth where we had to try to meet that. We build a lot of these FEMA flood maps off these physical benchmarks that are on the ground, and those benchmarks might not be the best equipotential elevation, but unfortunately, we still have to use them, right? Why? Because they were used in that original FEMA flood area model that they did when they did their flood study, when they did their cross sections of that bayou stream or creek or whatever. They used this specific benchmark, and maybe wrong or right, you almost have to go back to that one. So, kind of circling back to what you said before, you can use this GNSS and get this equipotential, but you need that redundancy, right, to go back and potentially shoot an existing monument. Would you agree with that?
Oh, absolutely. I mean, connecting to the real ground, it's kind of like, grounding yourself in reality. You can talk about, okay, GNSS and geoid models and all this other kind of stuff, but the rubber hits the road. You gotta tie it to the ground, and that's kind of the way of confirming what you're doing when you can check in on a benchmark, or confirm that, all right, that benchmark was based on an inappropriate datum, and now this is the correct value. I can't overemphasize the importance of connecting it to the physical ground. That's absolutely critical.
It again, circling back to your original statement, nobody wants a property corner that's just a coordinate. Nobody
Sure.
wants to know an elevation that's just something that comes from a magical geoid model. You need to tie it back to a point over here on a bridge nearby your house.
There you go. You want to be able to walk out there and see it. And maybe it'll be a brass cap with a little dot in the middle, and you can say, yep, that's the thing, and these are the coordinates for it. But that physical thing, if you're just kind of walk out there as a patch of dirt, and somewhere in this dirt here is where that coordinate puts you. No, it's people want to see those physical items.
We talk at the end of here talking about the NGS software that they use to do a bunch of the conversions to be able to go from one datum to the next datum, and to calculate those scales and convergence. And even on the vertical, if you went from the two different vertical datums, you can actually see some of the transformation values in your areas. What I most appreciated when I used your book in my PhD dissertation was that the math was all laid out for me. Now, the data that I started feeding that gave me different answers sometimes than I was anticipating. So, you can't imagine the software is going to fix all the solutions that you have in this. So you can't just take the answers for face value. Would you say going back to this statement you've made earlier that you need some redundancy, right, in that scenario? Give me some thoughts on utilizing geodetic software to calculate things, and what kind of trust should we put in it versus how much should we be checking to make sure it gave the right answer?
Well, I mean, it a lot of it depends on the parameters of the project. If you're dealing with, let's say you've got a drainage issue and I'm thinking back to Richard Allen. He's in the Orlando area. It's in some areas it's just flatter than a board out there, and you get a 1 inch vertical change out there, and it's a great horizontal distance that it goes in there, and it's getting your local transformation connected to the ground in your area is really going to be most critical. NCAT, that transformation tool, it uses data from a very wide area, but it may not have picked up exactly the benchmark or the local project points that you're working from. So you can get let's say an elevation transformation from NCAT that looks pretty good, and maybe if you're just doing some I don't know, rough contours for some nominal topographic mapping of some sort, that may be fine. But if you're starting to design a gravity flow sewer system, and you really need to make sure this is done accurately, then I would go on the ground and find local benchmarks. Perhaps do what I think you're talking about, is do your own transformation in that area, and tie it to the monuments that you have nearby. You will, I mean, for the highest accuracy, making sure you follow gravity and all that kind of thing, I would really recommend it that way. General mapping, sure, just the NCAT tool does a very fine job. I just wouldn't trust it if you're trying to tease out, a couple hundredths and that. It's a little too large, not a fine enough resolution for that.
Yeah, and that could put you in or out of a flood zone or a floodway, or have your home built below the required heights that we need. So, verify and check and get to know your own area, model, and understand the coordinates and monuments and everything in your own area. The local knowledge has a big value.
Sure. Well, and my goodness, this was some time ago, but I remember a Trimble rep giving us a talk about how if you want to do elevation surveys with a Trimble receiver, you would create essentially a local model, check into some local benchmarks, and have the the physical ground measurements determined, and it would in the software, it would use that as kind of a local frame, and then get your other elevations relative to those local points.
Yeah.
So for the highest accuracy, at least within a small relative area, definitely connect with those physical points on the ground.
Well, great. I think this was a perfect, good intro for learning about coordinate systems and datums and projections and how we use them in surveying and mapping from that standpoint. There's lots of other courses that are available online. As you pointed out, taking a good course with the NGS and some of theirs that they have, a little more detailed on their geodesy, but it's a growth process. You can never stop learning about coordinates and projections. And Dr. Dewitt, I appreciate all your time today and your comments. These have been very helpful. This concludes the Florida Surveying and Mapping Society Map Projections and Plane Coordinate Datums Continuing Education Credit course.